Welcome to the Deep Dive. Today we're plunging into a truly monumental geological era, one that really lays the groundwork for so much of Venezuelan geology,
Wow.
the Paleozoic.
That's right.
And for you, our listeners, especially those with a keen interest in geochemistry and regional geology, this is going to be, well, an immersive exploration. We'll dig into the formative processes that sculpted Venezuela's subsurface and its mountain ranges. So get ready. We're going to try and unravel some of the complex secrets locked away in rocks and orogenies from hundreds of millions of years ago.
Yeah, our mission for this deep dive is pretty clear. We've got this wealth of material shared with us, and the goal is really to extract the most crucial nuggets of knowledge about the Venezuelan Paleozoic.
Okay.
We're going to focus on the sequence of geological events, which is quite intricate, the distribution of the rocks, their specific lithological and paleontological characteristics, and of course the massive impact of the major orogenies.
Right. The big mountain building events.
Exactly. And by the end, the idea is not just to understand what happened way back when, but also why these ancient events are so fundamentally relevant to the geological setup we see in the region today.
Exactly. Think of this as your shortcut to being not just well-informed, but deeply insightful. We're aiming for specifics, enough detail to satisfy any geoscientist's curiosity, and really allow for a richer understanding of the geochemical analyses being done today.
Okay, so to kick off this deep dive, we really need to anchor ourselves in geological time, the Paleozoic era. It's just a vast stretch, isn't it? Roughly 350 million years.
It's huge, yeah, starting around 600 million years ago, marking the end of the Precambrian, all the way up to about 250 million years ago, which takes us right to the doorstep of the Triassic.
That timescale alone gives you a sense of the sheer immensity and, well, the diversity of events we're going to tackle. Absolutely. And what's really fascinating in the Venezuelan context is that this whole story of Paleozoic sedimentation, it's not just some smooth, continuous process. It's actually bookended, encapsulated and profoundly shaped by two continental-scale orogenic events.
Right, these massive collisions.
Massive collisions, yeah. Deformation events that didn't just define the beginning and the end of the era there, but also dictated the distribution and the very character of the rocks we find today.
Let's talk about the first one then. At the end of the Precambrian, roughly 600 million years ago,
Right.
we have the Caledonian orogeny. What did this actually do for the Venezuelan Paleozoic? How does an event like this sort of prepare the ground for what comes next, sediment-wise?
Well, the Caledonian is essentially a tectonic closing act for the previous era. You have ocean basins collapsing, microcontinents or island arcs colliding. It culminates in the assembly of larger land masses. For the Venezuelan Paleozoic, its impact is fundamental because it created new topography, new mountains. And as soon as you have mountains, they start to erode intensely. Imagine vast emerging ranges getting hit by physical and chemical weathering. So geochemically, this means the very first sediments laid down at the start of the Paleozoic in basins next to these Caledonian ranges, they carry a distinctive geochemical fingerprint.
Okay, so what kind of fingerprint are we talking about?
We're talking detritus, rich in quartz, feldspars, resistant accessory minerals, all derived from highly evolved Precambrian igneous and metamorphic rocks. Provenance studies using isotopes like neodymium, the epsilon values, and strontium, the 8A786 ratio, in these sediments, they allow us to actually trace the composition of that ancient continental crust that got crunched up and eroded.
Wow.
It gives us a direct window into the tectonic architecture of the Rodinia supercontinent right before it started breaking apart. Even things like placer deposits, gold or tin, could hint at pre-existing mineralization in that orogenic belt.
And then at the other end of the Paleozoic era, we have the Hercynian orogeny, closing things out around 250 million years ago. How did its activity and impact compare to the Caledonian in Venezuela?
If the Caledonian was the prologue, the Hercynian was definitely the dramatic final act, a real climax. It marks the end of the Permian, start of the Triassic, and this orogeny was an event of incredibly intense compression. And its impact was widespread, not just in Venezuela, but globally, tied into the assembly of the Pangea supercontinent.
Right, Pangea.
Yeah. So in Venezuela, it radically redefined the geography and the structure. It was a continental collision process that led to massive crustal shortening and thickening. This generated widespread regional metamorphism, the formation of huge thrust faults, kilometer-scale folds.
Give us some tips.
It was. And geochemically, the release of fluids from rocks undergoing metamorphism during this process is super interesting. These fluids can mobilize and concentrate metals, forming hydrothermal mineral deposits. Things like stable isotopes, oxygen and carbon in carbonate rocks affected by this metamorphism can give us clues about the fluid composition and the temperatures reached.
It's fascinating that there's also mention of an intermediate, more localized orogenic event around 475 million years ago on the South Andean flank. How would we distinguish the nature of something like that from these massive continental collisions, and what sort of geochemical signature might it leave?
That's an excellent question because it highlights the difference between global scale and more local processes. Continental events like the Caledonian and Hercynian result from large scale plate collisions, closing oceans, prolonged subduction, affecting huge areas. A local event like the one mentioned for the South Andean flank probably had a more specific origin. Maybe the abduction of a piece of oceanic crust, or the collision of a smaller island arc, or perhaps just the reactivation of an old zone of weakness in the crust. Geochemically, a localized event could generate magmas with very specific isotopic and trace element signatures. These would reflect maybe a more heterogeneous crustal source or even incorporation of mantle material in varying
So
amounts.
the different flavors of magma.
Exactly. If it was, say, an abduction event, you might expect to find mafic and ultramafic rocks of oceanic origin thing with distinct rare earth element patterns. If it involved arc magmatism, its igneous rocks would show enrichments in large ion lithophile elements, LILEs, and depletion in high field strength elements, HFSEs, that's typical of subduction zones.
Right.
And the localized compression could have triggered migration of metasomatic fluids, altering nearby rocks in very specific ways, maybe showing up as geochemical anomalies of gold, copper, or molybdenum.
So the big picture then is that these orogenic events aren't just isolated chapters. They act more like tectonic parentheses, encapsulating all the Paleozoic sedimentation, driving this cycle of uplift, erosion, deposition, and then new deformation. Is it fair to call it a constant engine of crustal recycling?
Yes, I think that's a very good way to put it. That cycle is fundamental to how the Earth's crust evolves. Each orogeny doesn't just deform what was already there, it also produces the raw material for the next phase of sedimentation. It's a continuous process of crustal recycling.
Okay.
The erosion products from one orogeny become the sediments that eventually get deformed and metamorphosed by the next one. Geochemically, this means continuous rehomogenization and differentiation of materials. For instance, silicate weathering during erosion consumes atmospheric CO2, impacting the global carbon cycle, while sulfide oxidation near the surface can release metals and acidify waters. The mineralogy of the detrital sediments from erosion gives us a chemical record of the source rock, letting us track changes in continental crust composition through the Paleozoic.
Let's shift to the paleogeography during the Paleozoic. It's mentioned that towards the end of the Precambrian and early Paleozoic, northern South America was presented as a positive area.
Hmm.
What does that tell us about the initial conditions in Venezuela, and how would that manifest geochemically?
A positive area, in paleogeographic terms, basically means a region of high relief, dominated by active erosion rather than deposition. So initially, northern South America was exposed land undergoing significant wear and tear through subaerial processes.
Okay, so it's being worn down.
Right. Geochemically, that translates into an abundant supply, of course, relatively immature detritus pouring into surrounding basins. The very first Paleozoic sediments nearby probably contained lots of fragments from Precambrian igneous and metamorphic rocks, with end and sear isotope signatures reflecting that old consolidated crust.
Makes sense.
The composition of these early sediments, like the ratio of quartz to feldspar to mafic minerals, gives us a direct window into the composition and weathering state of that Precambrian source landmass. Plus, resistant heavy minerals like zircons or monazites. They can be used for UPB provenance dating, revealing the ages of the source rocks in that positive area.
And then comes the marine transgression, the sea moving in. This seems to have been a progressive, long-lasting process covering vast regions of what's now Venezuela over millions of years.
It really was a gradual, persistent marine flooding. Over the next 250 million years or so, from the early to the late Paleozoic, that initial arm of the sea widened and relentlessly advanced northward, eventually reaching the Parija region.
Wow.
And this transgression continued into the late Paleozoic, submerging huge areas we now know as Valera, Trujillo, Táchira, and a significant chunk of the modern Lake Maracaibo area. This points to a widespread continental scale rise in sea level.
What would cause that?
Could be driven by factors like increased mid-ocean ridge spreading displacing water, or perhaps the melting of continental ice sheets. This progressive flooding created a whole spectrum of depositional environments.
Like what kind of environments?
Everything from high-energy coastlines through shallow platforms down to deeper, possibly anoxic basins. Each of these would leave its own distinct geochemical footprint. For example, deep marine facies tend to accumulate organic matter and clay minerals, while shallow platform facies might be rich in carbonates or well-washed sandstones.
Interesting.
And things like sulfur isotopes and pyrite formed in those anoxic settings can reveal bacterial activity and the redox conditions on the seafloor at different stages of this transgression.
And this leads to the formation of persistent shorelines, like the one bordering the Elbow region down to north of Santa Barbara de Barinas. What does the existence of these stable shorelines tell us about sediment distribution and its geochemistry?
A persistent shoreline is a strong paleo indicator. It tells us a stable, shallow coast existed for a considerable geological time. Sediment distribution along such a line is typically characterized by high-energy facies, well-sorted sandstones, mature, rounded quartz grains.
Beach sands, basically.
Pretty much. Depending on climate and local bathymetry, you might find evaporate deposits in coastal lagoons, or in wetter settings, coal in swamps or deltas. For a geochemist, these facies speak of high-energy conditions, wet-dry cycles, and potentially the concentration of resistant heavy minerals, rutile, zircon, monazite, which are great for provenance studies.
Right.
Plus, the cyclic exposure to air and water would promote oxidation, often leading to reddish coloration from iron oxides. The trace element chemistry in clays or iron oxides in these coastal rocks can vary dramatically depending on shoreline dynamics and river inputs.
I find the mention of Merida emerging as a large island and the swampy lowlands towards Perijá really striking, especially during a time of overall marine transgression. It suggests quite a bit of heterogeneity in the depositional environment. What are the implications of that diversity for the geochemical signatures in the rocks?
That's a key observation. Merida emerging as an island during a general sea level rise points to localized tectonic uplift, maybe a persistent structural high or a Precambrian massif that stayed above water. This high would act as a local sediment source.
Feeding sediment outwards.
Exactly, producing fringing facies. Coarser, less mature clastic deposits near the island, maybe with more feldspar and mafic minerals if the source was igneous or metamorphic. On the other hand, the swampy lowlands in Perijá suggest shallow areas with restricted water circulation, lots of plant-derived organic matter, and reducing conditions.
Sounds like a good place to make source rocks for oil and gas.
Potentially, yes. That's an ideal setting for forming hydrocarbon source rocks. So this environmental heterogeneity from high energy near the island to anoxic organic rich swamps translates into extraordinary lithological and geochemical diversity. You could expect clean, mature sandstones on the island's beaches, grading into carbonaceous shales and black mudstones rich in iron sulfides in the lowlands.
Fascinating range.
Absolutely. The organic geochemistry of those anoxic facies, things like total organic carbon, TOC, rock evil pyrolysis, biomarkers, would be critical for assessing their source potential and understanding the biological productivity of the time. Plus, the distribution of redox-sensitive trace elements like molybdenum, uranium, or vanadium would vary significantly between these environments, reflecting the water's oxygen levels.
And finally, this paleogeographic evolution seems to culminate in a relationship with the Hercynian orogeny, which kicks off with the formation of a new geosyncline. It feels like the closing of that grand cycle: erosion, sedimentation, deformation.
Precisely. It's the capstone on this huge geological cycle. The Hercynian orogeny starts with the formation of a new geosyncline, a classic term for a large, linear crustal depression. In modern plate tectonics, we might interpret that as a foreland basin, or maybe a rift basin, that activates and subsides rapidly.
Right, big trough.
A huge sediment trap, basically. It receives the detritus, the erosion products from the very mountains being uplifted by the orogeny itself. This massive accumulation of sediment in the geosyncline is crucial because those sediments would then be folded, faulted, and metamorphosed by the ongoing orogenic compression.
So the mountains feed their own basin.
In a way, yes. And from a geochemical perspective, the nature of that detritus in the geosyncline is incredibly important. It tells us about the composition of the mountains being eroded, their uplift and erosion rates, and the prevailing weathering processes. For example, volcanic debris might indicate nearby magmatic arcs, while abundant gneiss or schist fragments point to an origin in an older metamorphic belt.
How do you tease that apart?
Using geochemistry. Ratios of elements like titanium to niobium or zirconium to yttrium in these clastic sediments can help distinguish between felsic or mamethic sources. And the chemical index of alteration, the CIA, can quantify the degree of weathering. The geochemistry of geosynclinal sediments, being a mix of everything eroded from the source area, is a complex but invaluable geochemical archive of the orogenic history.
All right, now that we have that temporal and paleogeographic framework, it's crucial to understand how these Paleozoic rocks are actually distributed in Venezuela from a tectonic perspective. This distinction between autochthonous and allochthonous terrains seems fundamental for unraveling the story of how the continent was built.
Absolutely essential. Understanding this difference is key for any geologist trying to reconstruct the tectonic evolution of a continent. An autochthonous terrain, by definition, is one that's found in its original geological position relative to the South American continental plate. Basically, it hasn't moved significantly horizontally since it formed.
Like a puzzle piece that's always been in its spot.
Exactly that.
And according to the sources we have, the main location for these autochthonous terrains in Venezuela is in the subsurface, beneath the eastern basin and the Barinas-Apure Basin, specifically south of the Apure Fault.
That's correct. And the Paleozoic rocks in this terrain are primarily characterized by what are known as red beds. From a geochemical standpoint, the presence of these red beds is highly significant.
Why red?
Their distinctive reddish color comes from iron oxides, mainly hematite, which indicates deposition in a subaerial or very shallow oxygenated aquatic environment. These beds mark a critical geological milestone, the rifting, the pulling apart of Gondwana, which included South America and Africa, and Laurentian North America and Greenland.
So we're seeing the geological scar, essentially, of supercontinents breaking up.
Precisely, they're vestiges of a time of continental rifting.
How does that show up geochemically in these red beds? What can they tell us about the dynamics of that breakup?
The Cambrian sequences preserved in the structural lows of these basins hold the key. The geochemistry can give us direct clues about the rifting process. For example, finding volcanic rocks like basalts or dikes with the latic affinities interbedded within the red beds would indicate crustal thinning and upwelling of mantle-derived magmas.
Oh, okay, magma's coming up.
Yeah, and the trace element and isotopic signatures and ensunar, again in the clastic sediments of the red beds, can reveal the nature of the continental crust that was being stretched and eroded along the margins of the separating continents. You can distinguish sediments derived from old continental crust versus those from younger magmatic sources associated with the rifting.
Interesting.
Also, changes in clay mineralogy within these beds, maybe from smectite to elite, can indicate burial progression and thermal maturation linked to the development of the rift basin. And if you find evaporites like salt or gypsum associated with the red beds, that suggests arid, restricted conditions typical of early rift environments.
And then, in contrast to these autochthonous terrains, we have the allochthonous ones. These are blocks of crust that, by definition, have moved a long way from where they originally formed and then got tectonically stitched onto an existing continent.
That's the concept. And the key criterion for discriminating these allochthonous terrains is the age at which they were tectonically attached or sutured onto northern South America. This timing is crucial because it lets us reconstruct the complex evolution of continental margins, which are dynamic zones of convergence and collision.
So they arrive at different times.
Exactly. Based on our sources, these terrains can be broadly classified by when they arrived, some during the early Paleozoic, others in the late Paleozoic, and finally the most recent ones incorporated from the late Mesozoic onwards. Now, while the material we have focuses mostly on that later Mesozoic accretion,
Right.
it's important to remember that earlier suturing events, back in the Paleozoic, definitely happened too. Identifying them is just much more challenging.
Why is that?
Well, these earlier Paleozoic terrains are likely fragments, bits of island arcs, microcontinents, accretionary complexes that have been heavily deformed, metamorphosed, and eroded by later orogenies. Their original boundaries and geochemical signatures might have been overprinted or even erased by multiple tectonic and metasomatic events. It makes them much harder to delineate and characterize.
And the most recent and perhaps most extensively documented of these arrivals is the Caribbean mountain system. This represents the last major allochthonous terrain sutured onto northern South America. How extensive is this system, and what ages of Paleozoic rocks have been identified within it?
Correct. This system is geographically vast. It stretches all the way from the Guajira Peninsula, underlies the Gulf of Venezuela, includes the Paraguana Peninsula, and continues eastward along the Cordillera de la Costa right out to the Paria Peninsula.
Wow, that's a huge swath of territory.
It is. And the Paleozoic rocks identified within this terrain range in age, from the Devonian to the Permian. That significant age range itself tells you it's not just one simple monolithic block, but likely a complex assembly of different fragments that formed over a considerable time span somewhere else before they arrived and got accreted.
Okay, this is where it gets really interesting for me. From a geochemical perspective, how can you actually tell that a terrain is allochthonous and not just part of the original continental plate?
Beyond geological mapping, what kind of hard evidence do geochemists look for to confirm its foreign origin?
Right, it's really a multi-proxy approach that allows us to infer that a terrain didn't form where it sits now. The clues are multifaceted. First, there's the age of the rocks. If the ages within a terrain don't match the known geological history of the adjacent continent for the same period, that's a strong flag.
Okay, age mismatch. Second, the lithological facies. An allochthonous terrain often contains a sequence of rocks, sedimentary, igneous, or metamorphic, whose facies are inconsistent with those on the adjacent continental margin at the same time. For example, finding oceanic rocks like ocean floor basalts, MORB, or serpentinites, or island arc rocks like andesites or tonalites,
Yeah.
sitting on what should be a passive continental margin is a clear signal of allochthony.
And that's where the geochemistry comes in strongly.
Absolutely, it's a gold mine. Strontium, neodymium, and hafnium isotopes in igneous and sedimentary rocks provide the fingerprint of the magma source or the detrital source. If these fingerprints don't match the South American craton, we know they came from elsewhere. For instance, oceanic island arcs typically have more juvenile N and HF isotopic signatures, meaning more positive epsilon and HF values, compared to the ancient continental crust of the craton.
Okay.
Even lead isotope ratios in sulfide minerals like pyrite or galena can provide crucial information about the provenance and the metallogenic environment.
And I assume the tectonic structures themselves are vital clues in piecing this complex history together.
Totally vital. The presence of clear suture zones, these are large-scale shear zones where different crustal blocks are joined, and major thrust faults are compelling evidence that a block has been accreted. Rocks within these suture zones often show complex polyphase deformation and sometimes high-pressure, low-temperature metamorphism.
Like blueschists.
Exactly. Finding minerals like leucophane or jadeite in blueschists is indicative of subduction or collision environments. And studying the geochemistry of fluids released during metamorphism in these suture zones, say fluids that carried gold or base metals, also gives us clues about the accretion process and the fluid-rock interactions during collision.
So it's a real detective story using multiple lines of evidence.
It really is. All this allows us to reconstruct the history of how these blocks were added on. This process, terrain accretion, is fundamental to continental growth. It's how continents increase their size and complexity over geological time.
Okay, having set that broad tectonic canvas, let's now dive into an even deeper lithological journey. We'll explore the very fabric of the Paleozoic, the rocks themselves, and the ancient life they preserve, to understand how their specific features reflect the evolving environments of each subperiod in Venezuela. Let's start with the early Paleozoic, the foundations and the first traces of complex life.
Sounds good. The early Paleozoic, covering the Cambrian through the Ordovician, is a crucial time in the geological record and for the emergence of complex life. One of the key formations here is the Murallus Formation. Lithologically, it's described as carbonaceous phyllites and greenish-gray phyllites with massive to slightly schistose phylitic metasiltstones interbedded with quartzites.
Okay, what does that tell us?
Well, that description immediately suggests a protolith, an original rock type of shales and siltstones that underwent low-grade metamorphism.
And what about the fossils? The mention of trilobites, specifically Parabolina argentina, is quite specific.
Yes, the presence of trilobites, and Parabolina argentina in particular, is an excellent biostratigraphic marker for the late Cambrian. Finding them in carbonaceous and greenish-gray phyllites points towards a middle to deep shelf marine environment, conditions that supported benthic marine life.
And geochemically, what do carbonaceous and greenish-gray imply?
For a geochemist, carbonaceous phyllites is interesting because it implies the presence of organic matter, likely marine in origin. If well preserved, these rocks could have potential as hydrocarbon source rocks, although the metamorphism might have overmatured the organics. Trace element chemistry, things like vanadium, nickel, molybdenum, and carbon isotope ratios in these phyllites, can tell us about the ocean's paleoproductivity and anoxic conditions on the seafloor back in the Cambrian.
And the greenish color?
That usually suggests reducing conditions for iron, indicating low oxygen environments. You might expect minerals like pyrite to form in these sediments too, and their sulfur isotopes could reveal whether the sulfur source was marine or terrestrial.
Next up is the Saracone Formation, with phyllites and metasiltstones grading into quartzites and schists, and notably, hornfels dominant in the upper levels.
Right, the hornfels here is a dead giveaway for contact metamorphism. It strongly suggests the intrusion of a magmatic body nearby, which essentially baked the surrounding sedimentary rocks.
Okay, so heat from magma.
Exactly. Geochemically, forming hornfels involves specific mineral reactions under high temperature but generally low pressure. These reactions can mobilize elements, release hydrothermal fluids, and drastically alter the rock's composition. For instance, hydrothermal alteration linked to the intrusion could have introduced or leached metals, leaving a distinct geochemical signature of enrichment or depletion in certain elements.
Can you tell how hot it got?
Sometimes, yes. Mineral zoning around the intrusive, say from andalusite to cordierite or biotite, can indicate the thermal gradient, and mineral thermometry studies based on the composition of the metamorphic minerals themselves can give us pretty precise estimates of the temperatures reached during that intrusive event.
Then there's the Canyote Formation, described with micaceous quartzites, interbedded with arcosic metasandstones, cornubianites, and lenses of metaconglomerates.
This description paints a picture of a metamorphosed clastic sequence that saw significant deformation and recrystallization. The quartzites point to a quartz-rich source and a mature sediment, typical of high-energy environments. But the arcosic metasandstones suggest a granitic or felsic source and relatively rapid transport or an arid climate that prevented complete feldspar weathering.
And the cornubianites.
Like hornfels, those indicate contact metamorphism, reinforcing the idea of local magmatic intrusions. The metaconglomerates show larger clasts were present, implying higher energy depositional environments, perhaps near a source area or in a river channel. The geochemistry of those arcosic metasandstones would be key for detailed provenance studies.
How so?
Using things like rare earth element, RE geochemistry, or UPB dating of detrital zircons, you could pinpoint the exact igneous and metamorphic sources of the sediment. Ratios like lanthanum meterdium, LAY, or the europium anomaly, UOU, in the REEs can indicate if the source was felsic, mephatic, or if feldspar fractionation occurred during weathering and transport.
Moving on to the Cerro Azul section, described as a greenish phylitic sequence with no fossils found. What are the implications of no fossils for dating or environmental interpretation? And what might the greenish color tell us?
The lack of fossils in Cerro Azul is a significant challenge for biostratigraphic dating, forcing us to rely on other methods. It could mean conditions weren't right for preserving life, maybe too high energy, destroying remains, or paradoxically, an extreme anoxic environment inhibiting larger life forms.
But the rock itself tells a story.
Definitely. A greenish phylitic sequence is very indicative. The green color usually points to minerals like chlorite, epidote, or serpentine formed under low-grade metamorphism or advanced diagenesis. These contain iron in its reduced state, Fe2+. So this points to an original environment with suboxic or anoxic conditions, followed by low-grade metamorphism.
So how do you date it then?
Without fossils, dating leans heavily on isotopic methods. Things like argon-argon dating on micas or UPB dating on detrital zircons to get maximum depositional ages, or dating the metamorphic event itself. The lack of fossils might also suggest a continental or transitional depositional setting where marine fossils would be scarce anyway.
Now, Caparo, with fossiliferous siltstones and some conglomeratic sandstones, and importantly, graptolites, trilobites, and brachiopods.
The graptolites here are really significant. They are excellent index fossils, both benthic and planktonic types, for the Ordovician and Silurian, allowing for high-resolution biostratigraphy. Along with trilobites and brachiopods, they clearly indicate a marine environment, probably a shelf setting with varying energy levels.
Why varying energy?
The siltstones suggest lower energy fine material settling out, but the interbedded conglomeratic sandstones could represent sporadic higher energy events, maybe turbidity currents, storm deposits, or pulses of coarser sediment from a nearby source. Geochemically, these fossil-rich rocks could potentially be organic-rich source rocks if anoxic conditions allowed preservation.
What else can the fossils tell us?
Oxygen and carbon isotopes from the brachiopod shells can provide detailed info on Paleocean temperature, salinity, and global carbon cycles during the Ordovician and Silurian. Trace element studies in the siltstones can help track sediment provenance and weathering changes.
And then El Horno, featuring siliceous shelly limestones, shales, and silty sandstones, also with brachiopods.
This mix of shelly limestones and clastic shale siltstones suggests a shallow to mid-depth marine platform influenced by terrigenous clastic input. The shelly limestones indicate high biological productivity from organisms with calcareous shells, often linked to warm, well-lit waters.
What does silicious mean here?
It could refer to biogenic silica, like sponge spicules or radiolarians, or fine-grained detrital silica. The brachiopods again confirm an open marine setting. Geochemically, these limestones can reveal ocean pH and carbonate saturation conditions, maybe evidence of oceanic anoxic events impacting organic matter preservation and silica deposition. Strontium isotopes in the carbonates can help correlate the sequence with global seawater snur curves, offering a chemostratigraphic dating tool. And if the silica is biogenic, it might point to periods of high primary productivity.
Now for a controversial one. The association tostos. It's a sequence of metamorphosed sediments, slates, phyllites, schists, fine-grained gneisses, massive silicious rocks, and amphibolites, dominated by phyllites and schists. But the big debate is its age.
Right. This is where the geochemical puzzle gets really intriguing. The different age assignments: late Precambrian, according to Shegum back in '69, early Paleozoic based on field relations by Cannelone and Garcia, and late Paleozoic by Bilizia and Pimentel due to similarities with Mukuchachi, they just underscore the complexity of chronostratigraphy in metamorphic terrains and the critical need for multiple lines of evidence.
So from a geochemical standpoint, what do those rock types tell you?
The metamorphic nature schists, gneisses, and amphibolites indicate significant deformation and recrystallization under considerable pressure and temperature. The amphibolites, in particular, result from metamorphism of mafic rocks, like basalts, dikes, or gabbros. This suggests magmatic activity or tectonic processes involving mantle-derived material. Their presence implies a different protolith compared to the clastic sediments.
So how do geochemists tackle these fundamental dating discrepancies?
This is basically daily bread in geochronology and isotope geochemistry. When you have significant disagreements based on field relations or lithological correlations, isotope geochemistry becomes the most powerful tool. Methods like UP dating on zircons, both datrital ones in the original sediment and newly grown metamorphic or igneous ones, argon dating on micas and amphiboles, or samarium neodymium dating on whole metamorphic rocks can provide robust absolute ages.
Give me an example.
Okay, detrital zircons in the tostos, phyllites, and schist could reveal the age of the original source rocks that were eroded, giving a maximum depositional age. Whereas dating newly formed metamorphic minerals like garnet or mica would give the age of the metamorphic events themselves. If we date the amphiboles in the amphibolites, that could tell us the age of metamorphism or possibly even the age of the original mafic protoliths.
And resolving this age is critical.
Absolutely vital. It drastically changes our interpretation of the region's tectonic and paleogeographic history. If Tostos is early Paleozoic, it might be part of an early continental margin. If it's late Paleozoic, it's intrinsically linked to the Hercynian orogeny and its collision processes. Even things like oxygen and hydrogen isotopes in fluid inclusions within the metamorphic minerals can indicate the origin of fluids and their interaction with the rocks during metamorphism, crucial for understanding associated hydrothermal activity.
Finally, for the early Paleozoic, we have the Grupo Cachiri, which includes several formations: Los Quineos, Caño Grande, Caño del Oeste, and Campo Chico. Seems like a varied package.
It is. The Cachiri group presents a diverse lithostratigraphic sequence, indicating significant changes in the depositional environment over time. Los Quineos formations, the breccias, silty shales, interbedded sandstones, and then black limestones and silty marls towards the top suggest maybe rapid proximal sedimentation initially, perhaps near an uplifted area in an alluvial fan or fluvial setting.
Those black limestones sound interesting geochemically.
They often are. Black limestones can be rich in organic matter, type 2 or 3 kerogen, deposited under anoxic or dysoxic conditions, hinting at hydrocarbon source potential. Caño Grande formation with sandstones and recrystallized bioclastic limestones and shales suggests a shift to a shallow marine platform environment with strong biogenic influence. The recrystallization indicates some diagenetic or metamorphic overprint.
Right.
Caño del Este formation with shales and alternations of silty sandstones and dolomitic limestones reinforces the platform idea, but with clastic pulses and dolomitization processes. Dolomitization impacts porosity and permeability, which is key for fluid storage. Lastly, Campochico Formation, with ferruginous gray wax interbedded with siltstones and limestones, and being barren of fossils, points towards immature, iron-rich sedimentation, possibly in a fluvial or deltaic setting with high sedimentation rates.
And again, no fossils makes dating tricky.
Exactly. Like Cerro Azul, it hinders dating and might indicate environments hostile to life or preservation. The geochemistry of those iron-rich gray wax, though things like Fe, T, Al, and REEs, could help us understand the weathering of the source and the redox conditions during transport and deposition.
Let's move into the Middle Paleozoic. This covers the Devonian Mississippian, one of the shorter periods of the era, and remarkably, it seems quite elusive in Venezuela's geological record.
That's right. The scarcity of Middle Paleozoic rocks is a distinctive feature, almost a geological enigma for Venezuela. It hasn't been found in the El Baúl region or on the South Andean flank. Devonian rocks haven't been identified in wells drilled in central Lake Maracaibo either. Its presence seems critically restricted to the Sierra de Perijá region.
So what does this significant lack of record imply for the paleogeography and plate tectonics of Venezuela during that time? What are the implications for a geochemist trying to piece together the continent's history?
This scarcity has major implications, leading to a key paleogeographic inference. It suggests a widespread phase of either non-deposition or, more likely, active and persistent erosion across much of Venezuela during the Devonian Mississippian.
So the land was being worn down, not built up?
That seems likely. It could be the result of regional uplift exposing the crust to subaerial erosion, or maybe most of northern South America was configured as a topographic high, where sediment transport dominated over accumulation in basins.
And geochemically.
It means the sedimentation cycle was interrupted or rerouted. If there was uplift and erosion, you'd expect sediments deposited in basins adjacent to Venezuela during that time to carry a distinct geochemical signature of the Precambrian or early Paleozoic rocks being eroded within Venezuela. You could see that in detrital mineral provenance and isotope signatures.
So Perijá was special.
The Sierra de Perijá, being the only region with a significant record from this period, must have been a localized subsiding basin or a tectonically sheltered zone protected from erosion. Therefore, the rocks found in Perijá from this time have a unique geochemistry reflecting particular depositional conditions and tectonic history for that specific window. Studying paleosols or unconformities related to this non-depositional phase elsewhere could also yield clues about the intensity and duration of erosion and its impact on regional biogeochemical cycles like nutrient release or weathering patterns.
Finally, we arrive at the late Paleozoic, covering the Carboniferous and Permian. This period does have a more robust presence and is known from several regions in Venezuela, allowing us to reconstruct a more complete picture just before the final big orogeny.
Correct. Along the northern edge of the Guyana Craton, we find the Carrizales Formation. It's characterized by dark greenish to black argillites, dense, massive, and remarkably homogeneous despite occasional silty intervals, with local interbeds of sandstones and pebble conglomerates.
Black argillite sounds like another potential source rock situation.
It definitely raises a flag for geochemists. Black shales or argillites often indicate anoxic or disoxic environments, rich in organic matter, type 1 or 2 kerogen if marine, type 3 if continental, and can have significant potential as hydrocarbon source rocks. The overall homogeneity suggests a relatively stable depositional setting, punctuated by occasional higher energy events like turbidity currents. Organic geochemistry, TOC, rock evol, biomarker analysis would be crucial to assess its generation potential, organic matter type, and maturity. Carbon isotopes in the organic matter could also help pin down a marine versus terrestrial origin.
And down on the South Andean flank, we find several key formations for this period. First, the Mucuchachi Formation with slates and conglomeratic metasandstones and metaconglomerates.
The Mucuchachi Formation tells us about clastic rocks that have undergone low to medium grade metamorphism, hence the slates and metasandstones. The conglomeratic nature indicates a varied source area providing significant coarse debris, likely transported over relatively short distances. This suggests proximity to an active orogenic uplift zone.
What about its geochemistry?
Geochemically, the metamorphism likely affected the organic matter drastically, probably converting it to graphite, making its hydrocarbon generation potential negligible. However, its inorganic geochemistry major and trace elements would still be valuable for provenance studies of the source rocks. Using REE patterns or end and seron isotopes, for example, to determine the composition of the continental crust being eroded at that time. The presence of specific metamorphic minerals like chlorite, sericite, or biotite Can also give us clues about the pressure-temperature conditions reached.
Next, the Sabaneta Formation, described as a sequence of quartzose sandstones grading upwards into interbedded siltstones and sandstones.
This formation describes a gradual shift in the depositional environment, signaling an evolving paleogeography. The quartzose sandstones suggest mature, well-sorted sediment, typical of high-energy beach, coastal dune, or shallow shelf environments. This points to a stable quartz source and prolonged transport that removed less stable minerals.
And the change upwards.
The gradual transition to interbedded siltstones and sandstones towards the top indicates a progressive deepening of the environment, or a decrease in energy, perhaps a prograding delta, or a transition to a slightly deeper shelf. Geochemically, the maturity of the quartz sandstones means many labile elements were lost during weathering and transport, resulting in a simpler bulk chemistry dominated by SiO2.
So, less informative.
Not entirely. Trace amounts of heavy or resistant accessory minerals, zircon, rutile, tourmaline, can still provide clues about provenance and the source rock's alteration history. Oxygen isotopes in the detrital quartz can also be used to track the thermal history of the source.
And lastly, for the late Paleozoic overview, the Palmerito Formation, with a sequence of shales, marls, and limestones, all reported as fossiliferous.
The Palmerito Formation is a biostratigraphic highlight for the Permian in Venezuela. The presence of fossils, including brachiopods, fusilids, and other marine organisms, is fundamental for accurate dating and reconstructing Permian marine platform environments.
What does the rock mix tell us?
The combination of shales, marls, and limestones suggests a marine platform setting, probably lower energy than where the quartz sandstones formed. The marls and limestones point to strong biogenic influence, significant carbonate accumulation mixed with clay material. The shales, if organic rich, could also be potential source rocks, depending on redox conditions.
And the fossils are key for more than just dating.
Absolutely. The type and diversity of fossils inform us about the salinity, temperature, water depth, and paleogeography of the Permian in this region. Isotope studies oxygen and carbon on the fossil carbonates can shed light on Permian paleoclimate and paleoceanographic conditions in Venezuela, maybe revealing oceanic anoxic events or shifts in the global carbon cycle. It really is fascinating how the lithology, fossils, and geochemistry together paint such a rich, detailed picture of the depositional environments for each Paleozoic subperiod.
And so we arrive at the grand finale of the Paleozoic,
Yeah.
the Hercynian orogeny. This event doesn't just mark the transition from the Paleozoic to the Mesozoic in Venezuela. It was, as described, a very active tectonic event characterized by intense compression that radically transformed the region's geography and structure. How can we visualize that intense compression, and what are its deeper implications for the continental crust from a geochemical perspective?
You can picture that intense compression as two or more large continental blocks, or maybe a series of microplates and island arcs colliding and converging. They're essentially squeezing the crust caught between them in what you could call a gigantic tectonic vise. This results in massive crustal shortening and thickening, which in turn triggers a cascade of significant geological events. Geochemically, this deep compression doesn't just fold and fault rocks on an unprecedented scale, it also subjects them to high-pressure, high-temperature regimes, setting off large-scale mineralogical and chemical transformations. The directional pressure, for instance, encourages minerals to recrystallize with a preferred orientation, leading to foliation and schistosity in metamorphic rocks. This directly impacts their permeability and therefore how fluids migrate through them.
And one direct consequence of this collision are the syntectonic granitic intrusions emplaced at supercrustal levels, affecting the Venezuelan Andes and the Sierra de Perija. From a geochemical viewpoint, how do these granites serve as archives? What information do they hold about the crust being recycled or formed during this orogeny? And what can they tell us about deep magmatic activity linked to the collision?
Oh, absolutely. These syntectonic granitic intrusions are indeed a crucial and distinctive geochemical signature of the Hercynian orogeny in the Venezuelan Andes, especially the central region and in Perija. These granites typically form from the partial melting of the thickened, heated continental crust itself, warmed by the orogenic compression, or sometimes from mantle-derived magmas that ascended and interacted significantly with that crust.
So they hold clues about their origin.
They're exceptional archives of information about their source and the processes that generated them. The key lies in their major and trace element composition, and particularly their isotopic ratios. We analyze strontium isotopes, 87 Sr, 86 Sr, neodymium, and hafnium, niobium. For example, high initial 87S R86S ratios combined with low or negative N values are typical of magmas derived primarily from melting old sediment-rich continental crust. That points to extensive recycling of pre-existing material.
And if the mantle's involved.
Conversely, if there's a significant mantle contribution, the isotopic signatures will shift towards mantle-like values lower, 87 SR86 Asir, and more positive values. Certain trace elements, like yttrium, ytterbium, or tantalum, niobium, can also help distinguish between granites from purely crustal sources, S-type, versus those with mantle or subduction zone influence, I-type or A-type.
Sorry.
Plus, the fact that these syntectonic granites were emplaced at supercrustal levels implies the magma rose rapidly through the crust, likely using zones of weakness or fractures created by the orogenic compression itself as conduits. Studying fluid inclusions trapped in the minerals of these granites can even reveal the composition and temperature of the magmatic and postmagmatic fluids, which is relevant for associated mineral deposit formation. These analyses give us a direct insight into crustal accretion, recycling, and the interplay between mantle and crust during the Hercynian orogeny.
And regional metamorphism is another fundamental consequence of the Hercynian. What kind of metamorphism in mineral assemblages might we expect, given that intense compression and associated intrusive activity?
Given the intense compression and magmatic intrusions, we'd expect regional metamorphism of the orogenic type. This is characterized by depth. In the Paleozoic rocks of Venezuela's central region, this would translate into a specific progression of metamorphic facies.
What would that look like?
At the lowest grades, you'd see slates and phyllites developing, with low temperature indicator minerals like chlorite and sericite. As pressure and temperature increase with burial and compression, the rocks would evolve into schists. There you might find minerals like biotite, garnet, staurolite, and kyanite, indicating medium-grade metamorphism.
And at the highest grades.
Especially near the granitic intrusions where the thermal kick is strongest, you could find gneisses containing sillimanite or cordierite, depending on the specific pressure-temperature path and the original rock composition, bodolith. Geochemically, this metamorphism causes massive mineral recrystallization and, crucially, mobilizes fluids. This can lead to significant redistribution of elements. For instance, new mineral growth can sequester certain elements like boron going into tourmaline, or rare earths into garnet, while other elements like volatiles, H2O, CO2, and some metals get liberated and transported by hydrothermal fluids.
And these fluids can travel.
Yes, they can migrate through the crust and precipitate minerals in lower pressure zones, potentially forming valuable mineral deposits. Studies using mineral thermobarometry based on the chemical composition of coexisting metamorphic minerals are essential for reconstructing the PT conditions of this metamorphism, allowing us to trace the pressure-temperature time, PTT paths, the rocks experienced during the orogeny.
This must be fundamental for understanding the region's current structural architecture, right? I mean, how geochemists use these structures.
Completely fundamental. The intense tectonic deformation generating faults, folds, and a host of related structures is the direct physical expression of that intense orogenic compression. The development of cleavage, those planar weaknesses in metamorphic rocks forming perpendicular to maximum compression, and thrust planes, low-angle faults where huge rock masses slide horizontally are clear evidence of the direction and magnitude of the compressive forces.
And for a geochemist.
For the geochemist, these structures are far more than just geometry. They critically control fluid circulation in the crust. Fault zones and cleavage planes act as preferential pathways for hydrothermal fluids. This can lead to the formation of mineral veins carrying precious or base metals or cause pervasive geochemical alteration of the surrounding rocks. Deformation can also directly affect the maturation of organic matter in pre-existing sedimentary rocks by increasing temperature and pressure, impacting hydrocarbon generation and migration. So the distribution of geochemical anomalies in the field can often be directly tied to the structural architecture inherited from the Hercynian orogeny.
And naturally, an orogeny of this scale led to major paleogeographic changes. How did the Venezuelan landscape get reconfigured?
The Hercynian caused a dramatic reshaping of the continental landscape in Venezuela. Firstly, there was significant uplift of the northern edge of the Guayana Craton, turning it into a major, persistent source of sediment for adjacent basins. Secondly, the sea retreated considerably northward from western Venezuela, implying a large-scale marine regression, likely due to the widespread continental uplift.
And the Andes.
Crucially, this is when the topographic uplift of the ancestral Andean Cordillera occurred what's known as the Merida Arch, oriented roughly NNW-SSE. It's important to stress this isn't the modern Andes we see today, but its geological precursor, an embryonic Andes forged by Hercynian forces. This new topography profoundly influenced drainage patterns and sedimentation for subsequent geological eras.
Okay, so if we pull all these threads together, the granitic intrusions, the metamorphism, the deformation, the paleogeographic shifts, what does it all mean for the geochemist trying to unravel the history of sediments, fluids, or mineral deposits in Venezuela? How do these layers of events overlap, and how can they be sort of geochemically dismantled?
That really gets to the core of geochemical investigation in a complex orogenic belt like the one left by the Hercynian. These paleogeographic and tectonic changes control a suite of fundamental geochemical processes that impact crustal composition and resource formation. The uplift of the Guyana Craton and the ancestral Merida Arch meant new sources of detritus became available for post-Hercynian sedimentation, carrying different provenance signatures than the earlier Paleozoic rocks.
So the sediment chemistry changed.
Drastically. The chemistry of sediments in adjacent basins, like the Barina-Zapura Basin, would change, reflecting this new provenance. You can track this using trace elements and NDSR isotopes in the clastic sediments. The sea retreating implies a fundamental shift from marine to continental environments, altering redox conditions and the type of organic matter being preserved. This directly impacts organic matter maturation and source rock potential, shifting maybe from marine type 3 kerogen towards continental type 3. Furthermore, fluids expelled during compaction and metamorphism at the orogeny climax would migrate through these newly formed structures, interacting with rocks, altering their composition, and very importantly, potentially forming mineral deposits. Gold, tin, tungsten are often associated with these synorogenic granites in contact metamorphism. Stable isotope studies, oxygen, hydrogen, sulfur, and hydrothermal minerals and fluid inclusions allow us to characterize these mineralizing fluids. The Hercynian orogeny is truly a key event that reset the distribution of rocks, the landscape morphology, and the chemical systems of Venezuela, preparing the stage for subsequent geological eras and leaving a profound geochemical imprint that's still being studied and explored today. Hashtag, tag, 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 outro.
Wow, what an incredible journey through deep time. From the formation of the very first marine sediments influenced by the Caledonian, right up to the colossal Hercynian orogeny that sculpted a new continent, we've really peeled back the intricate layers of the Venezuelan Paleozoic, exploring its distinct lithologies, the traces of ancient life they hold, and the orogenic processes that shaped it so profoundly.
Yeah, and what we've explored today isn't just distant geological history. These are literally the foundations upon which Venezuela's modern geology is built. Understanding these orogenies, the distribution of autochthonous versus allochthonous terrains, and the specific geochemical characteristics of each Paleozoic period.
Mhm.
It's absolutely fundamental for any geochemist looking to grasp the evolution of the crust, the formation of natural resources, or the region's biogeochemical cycles.
Right.
The geochemistry of these Paleozoic rocks gives us invaluable clues about mantle and crustal composition, ancient depositional environments, and the processes of continental recycling.
We really hope this deep dive has given you, our listeners, not just data and concepts, but perhaps a fresh perspective on the sheer complexity and richness of Venezuela's geological past. From those red beds telling tales of rifting continents to the syntectonic granites revealing deep crustal recycling, every detail brings us closer to a more insightful and applicable understanding.
And that detailed understanding of these formations and events is absolutely key for interpreting present-day geochemical analyses. For instance, in hydrocarbon exploration, identifying Paleozoic source rocks or understanding organic matter maturation is crucial for predicting where deposits might be. In assessing geological hazards, understanding how Hercynian structures created faults can help us evaluate seismic activity on reactivated fault zones. And it's vital for researching the evolution of life through fossils and their isotopic signatures, and for understanding Earth's elemental cycles over geological time from carbon to metals. Every rock, every structure is a geochemical archive just waiting to be fully deciphered. This deep dive into the Paleozoic leads to a rather intriguing question. If the Hercynian orogeny was so critical in reorganizing the continent, forming new structures and crystal compositions, how might its scars continue to resonate today? Perhaps in patterns of seismicity, or even in the composition of the lithospheric mantle beneath Venezuela. And what advanced geochemical methods could we potentially employ to probe that connection more deeply?
That's a fascinating question to keep exploring, and a great reminder that the geological past is often the best map we have for understanding the present. Thank you for joining us on this deep dive. Until next time.